Good morning, all. Today is my second lecture. So, hopefully, today we also discuss some basic like yesterday. Tomorrow we will discuss research activity. We will focus specifically research which is going on here in our group. So, So we'll start from the discussion that we have made yesterday at the end of lecture, which was very nice discussion, and also we got some informative idea. So, sir, today sir is here or not? Devasi sir, that Devansu, what? Okay, so. Uh, if we start that yesterday we discussed about the questions, very nice pointed out by one of our participants. So why this direction is different? Is along the L value, you can get L value along one direction, and this that means this is K wave vector versus energy. Why different orientation of the lattice is used here? So the answer is that today it was unsolved. So let me clarify the doubt. So actually this figure is right. That means we can get this L value along 1 direction and X value along 1 0 direction. So for clarification, let's see for the specifically the students. So what about this? So where you can get this decay diagram from the brilliant zone. So as all of you know, suppose if you take a, yesterday I already told, if you take in a crystal, there are regular periodic arrangement of atoms, and due to overlapping of atoms with certain limitations, certain boundary conditions, that atomic overlapping of atomic arrangement will look like a multiple quantum well structure. So if you solve it, that means let the well is having length A and barrier having that width A and width B. Then in real space, if you take it, let the total length on both sides of one of the OL of a single OL is A plus B, that is this one. Then you can see if we solve this by using KP model, Penning model, then you can got the idea about the first brilliant zone. So which is extended let in along one direction, X direction, which is pi by L to pi by L, this negative sides. So if this is the first brilliant zone, and if you take, there are, in this way you get multiple number of many number of zones, the EK diagram will look like this. So this gives the idea of energy versus wave vector. This axis energy, this axis K. So if you take a two-dimensional structure in real space, so that means let that extended along Kx and Ky, and you solve this brilliant zone, then that brilliant zone will see it looks like this parabolic shape in the conduction band. So and if you take from this the constant energy surface, which is this one. So as yesterday pointed out, see the answer is that. So in a brilliant zone, actually there are multiple directions. If you go for the solution along this X value, you can get multiple value, X value, gamma value, L value, and they are not in a single direction. They are in multiple directions, like suppose 1 1 1 is a symmetric direction in this depending upon this lattice. So this that means uh, if you go for x direction along 100 x, if you move along 100 direction, you can get the x value in germanium. Similarly, if you go along 111 direction, you for the analysis of energy variation with respect to the wave vector, reach at the L value. So these x and L, this value, they are obtained at a different orientation. So for our simplicity, when we analyze, we just join it. That means from the, we take the x, this x value, and we take L value, and we combine, and we see this is the EK in joint. So actually, in EK diagram, this x and L, they are as they are obtained at a different directions. So that's why this one is right that we have shown yesterday. Okay, this is all about the yesterday's query. So so you can see here. So that means here, if you take this L value and if you zoom it, looks. So this is all about. So the today's presentation, but today's presentation will start from some basic idea and some information that obtained from the internet, that Nobel Prize, we got Nobel Prize in physics, particularly based upon our today's discussion, that is heterostructure and its related devices. Then we'll go for the band engineering, types of heterostructure. Then the important one is the modulation doping. Also, there are other doping, delta doping like this. And based upon the modulation doping, we will go for MODFET, that is modulation dope, field effect transistor, HEMT, that is high electron mobility transistor, and the quantum effects in heterostructure. Specifically, we'll see about how the density of states changes if we reduce the dimensions of the device, that is from 3D to 2D, then 1D and 0D. Finally, we will conclude. So this is the presentation layout of the today's presentation. So as you know, if we start from the semiconductor technology, that starts from the transistor. So these three fellows, that Shockley, Bardeen, and Bratton, they got Nobel Prize in 1956 due to their pioneer work on transistor. That means they have first discovered, that means invented, not invented the point contact transistor. So that means in 1947 at Bell, and they got Nobel Prize in 1956. So in a Nobel lecture, the Bratton, he expressed his view that the main point of this story is that now, as a result of the progress that has been made in the understanding of semiconductors, we have another model of a surface, namely a p-n junction in a single crystal of a semiconductor. So that means that junction, which was the contact junction, which was invented by these three fellows, then it changes the semiconductor diversity. So same in 1964, these three towns, Basov and that Proctor, they got Nobel Prize for their fundamental work in the field of quantum electronics, which has led to the structure of oscillators and amplifiers, which is particularly based on the major. So it is interesting that was discovered, that is microwave amplified stimulated emission of laser. So which is basically based upon the heterostructure. Similarly, in 2000, for basic work on information and communication technology, these three, Alfred, then Friomberg and Kilby, they got Nobel Prize. These two fellows, they got it for developing semiconductor heterostructure used in high speed and optoelectronics. Nowadays, we are getting very high speed data due to the this optical communication, and the main part is the you convert the electrical signal into optical, or you convert optical into electrical. That means the ILD, injection laser diode, which is that efficiency developed a lot after the development of semiconductor heterostructure. So that's why they got Nobel Prize. And the other one who will be, who invented or who made the first IC, Jack Kilby, for his part in the invention of the integrated circuit. But he got Nobel Prize too late, because in 1965 he made the first IC. He got in Nobel Prize in 2000. So regarding this heterostructure, the Professor Carlson of the Royal Society of Academy, he I quote that it is viewed as a prime moreover in the economic upswing our society has experienced over the past decade. So this year's Nobel Prize in Physics reward contribution to the early development of microelectronics and photonics, focusing on the integrated circuit or chip, as well as semiconductor heterostructures for laser and high-speed transistors. So that pioneer work on semiconductor heterostructures made a drastic change in the field of laser field, and that leads to also high-speed transistors. So these semiconductor heterostructures that can be regarded as a laboratories of two-dimensional electron gases. So the 1985 and 98 Nobel Prize in Physics for quantum Hall effects were based on such confined geometry, like heterostructure. So they can be reduced further to form one-dimensional quantum channels and zero-dimensional quantum dots for future studies. So this was the statement of speech by Professor Carlson of the Royal Studies Academy of Science regarding the semiconductor heterostructure and how it changes the future of lasers and high-speed transistors. So on a Nobel lecture by given Farmer, I quote that heterostructures, as I use the word here, may be defined as heterogeneous semiconductor structures built from two or more different semiconductors in such a way that the transition region or interface between the different materials plays an essential role in any device action. Often, it may be said that the interface is the device. That means we get the interesting property at the interface between two different material, which is that means the interesting property will arise at the interface of the heterostructure. So similarly, the Alfred got also Nobel Prize for this heterostructure, semiconductor heterostructure. I quote, it can be said that if the possibility of controlling the type of conductivity of a semiconductor material by doping with the various impurities and the idea of injecting non-equilibrium charge carriers were the seeds from which semiconductor electronics developed, heterostructures would make it possible to solve the considerably more general problem of controlling the fundamental parameters inside the semiconductor crystal and devices. That means band gaps, effective masses of the charge carriers, and the mobilities, refractive index, indices, electron energy spectrum, etc. So this shows the importance of heterostructure and how it can change the optical industry or this also high-speed electronics due to this heterostructure. So this is all about the Nobel Prize they got and their statement regarding the importance of heterostructure. So let me start first to know about heterostructure, the band engineering. Already I explained yesterday. We know as artificially, that means we can there are man-made structures, so we can change the band that like other engineering, we can change the band. So this is called band engineering. So that means before we go, as per the in general, when you go for a heterostructure, the vacuum levels will be aligned as per the this is so the vacuum level of the two materials of heterojunction that should be lined up, and let us consider two material, material A and material B, and this material A having low band gap EGA, that of EGB. So as their band gap is different, the parameter which is known as the electron affinity, that means the gap between vacuum level and conduction band, the electron affinity, there is a difference in electron affinity, and uh, and also there is another parameter which decides in band engineering is the work function, which is measured from the Fermi level uh, as a function of, and that work function can change by in terms of doping. If you change doping, then you can also change the work function. So in a heterostructure, so you can get a band offset in the conduction band as well as in the valence band. So in conduction band, the band offset, which is the EC of here, the in the upper is the conduction band of B material. So EC of B minus EC of A. That means the conduction band of the higher band gap material minus conduction band of the lower band gap material. You can directly got it from the material parameter, that is the electron affinity, which is equal to electron affinity of A minus electron B. So similarly, the delta EV, which is equal to EV of A, sorry, EV of A minus EV of B. So see one important thing here in this case, see, as the electron affinity of A, that means the low band gap material is the high as compared to the electron affinity of the high band gap material. So if you make a doping in the higher band gap material, then it can move to the low band gap material because the electron affinity is high or larger in the low band gap material, which we will see in a modulation dope structure. So that means to tune the band to band gap, we should know about the lattice constant versus the corresponding energy, because we cannot take any two binary or any two semiconductor and make a new type of material. There are certain rules. So that followed by the lattice constant with respect to their energy gap, which is a low at 4.2 Kelvin. So you see, there are different. These are semiconductor material, but they have different band gap. For example, if you say this gallium arsenide, so this gallium arsenide, and take another one is aluminum arsenide. So gallium arsenide, which is around 1.42, the aluminum arsenide, which is around 2.16 EV electron volt. And if you see the lattice constant, their lattice is approximately matched. The lattice constant gas and aluminum arsenide is approximately matched. So if you take gallium arsenide and aluminum arsenide and you can form gas, then it will be lattice match heterostructure. However, see another one. If you take a indium arsenide and take another, suppose here aluminum arsenide. So if you want to make a compound semiconductor by taking indium arsenide and aluminum arsenide, you can design in gas, indium aluminum arsenide. But on which material you want to grow indium aluminum arsenide, that will decide whether it will be lattice match or lattice mismatch. So if there is lattice mismatch, then you can get the strain. Yesterday I already told you, in 2000 onwards, in the CMOS technology, the strain technology has very emerging impact on semiconductor industry. So this, you see germanium, the lattice constant, and silicon. So if you make a compound semiconductor by taking silicon and germanium, and if you grow that silicon germanium over germanium, then it is a totally lattice mismatch. So it will give you strain. So when you go for band engineering, first you should analyze what is the lattice constant of that particular material and what is its corresponding energy. So then from this data, you you can judge whether it will be lattice match or lattice mismatch. If lattice mismatch, no problem, you can go for the strain. That means for this, you calculate the band gap by taking the strain effect. So based upon this, the band diagram of heterostructure is a heterostructure that we obtained at two different semiconductors when they are brought into physical contact, and we use the property of heterostructure, which are important in different devices, heterostructure devices like a FET, HBT, that is a heterostructure bipolar transistor, LED, lasers, etc. So depending upon the band gap and the band offset, conduction and valence band offset, they are classified into three types. One is a type 1, which is also called straddle, type 2, staggered, and type 3, that is called broken gap. So the heterostructures are of three types. This one is type 1, type 2, type 3. You can see in type 1, like if you grow a gallium arsenide over gas, or gallium antimonide over aluminum antimonide, or gas over gallium phosphide, then that heterostructure is type 1. Whereas this is for type 2, like if you grow indium phosphide over you grow aluminum indium phosphide over indium phosphide, or this, then you can get type 2. And if you grow indium arsenide over gallium antimonide, you can get type 3. So this is depending upon their overlapping of this delta IC and the delta IC. So I will explain in details. See here. See here. So in type 1, see this this is material A, this is material B, this is the vacuum level. So here the delta IC, that is the gap between the conduction band of higher band gap material minus conduction band of lower band gap material, which is delta IC. You see this delta IC and there is delta IB. And this material, the low band gap material, is totally within the energy gap of the high band gap. So this is the condition. If you see here, this EG high band gap material, and there is a low band gap material, and here the narrow band gap material is enclosed within between the wider band gap material. So here the gap is 1.8. Here the gallium arsenide having band gap 1.42. So if you see the delta IC, normally in this case the conduction band offset you can calculate by knowing the, which is normally in gas is 66% that of the delta Ig. What is delta Ig? Eg2 minus Eg1 will give you delta Ig. Similarly, the conduction band offset, normally it is taken as the 1/3, that is 33.3%, 1/3 of that of the delta Ig. This is delta Ig is Eg1 minus Eg2. So here, if you see, the signs of the band offset for the two band is opposite. That means if you say this delta IC, that means the ECB minus ECA, this is a positive quantity, whereas this delta IB, this is a negative quantity, because ECB is at a lower, ECA is at a higher level. So you will get a negative sign. So when the band offsets for the two band is negative, is opposite, then you will decide, or you can judge it that it is a type 1 heterostructure. Type 1 means that is the straddle. Here the delta IC is around 0.23 eV, and that delta IB is around minus 0.15 eV. Similarly, in case of type 2 and type 3, here both the band offsets have the same sign. You can see here, this is a gallium arsenide antimonide, and this is indium gallium arsenide. So here you make a heterostructure. So if you see, this is EC of material gallium arsenide antimonide. This is a conduction band of in gas. So this one is delta IC. Similarly, this the valence band of gallium arsenide and antimonide, and this is the valence band of indium gallium arsenide. And now, if you find the delta IB, this is higher. This is at this energy minus this, so it is both are having same sign. that is around 0.49 eV and 0.39. Similarly, if you take a type 3, then you can also obtain the band offset having the same sign. But interesting fact in type 3 is that this the offsets are so large that the gaps in the material don't overlap. It looks like a broken gap, broken. That's why it is called broken gap type. See, this is delta EC, this lower one is delta EV, and they don't overlap here. Here somehow it is overlapping, but here in type 3, it is totally not overlapping the conduction band offset and valence band offsets. So it is known as the broken type. And particularly for optical materials and transport property, no doubt all type 1, 2, 3 are used, but type 1 is very common, which is used for optical devices as well as transport property. So, uh, you can see in details this type 1, type 2, and type 3. So if you see, this is the band offset, delta EC, delta EV, and when you make the heterojunction, there is 2DG, two-dimensional electron gas will form. So here you can get the electron at the interface, and electron will be reside in the gallium arsenide layer. So, and if you form a superlattice by using this material, it will be seems like this. So similarly in type 2, here you can see the delta EC and the delta EV, and you can get here the two-dimensional electron gas. So similarly, that for broken gap, that is for type 3. So this last one gives you the superlattice if you form by using this semiconductor heterostructure, and this middle one, which is gives the band bending. So then another after band engineering, another fact comes is the modulus doping. So as you know, in classical devices means, for example, take a PN junction, which is a classical devices. So if you dope in the P-type material, that is, if you dope introduce, that means you want to introduce carriers. So you dope the region where electron or holes are desired. That means in the same region where you want electron and hole, you dope there. So what is the problem here? So when you dope, then that gives you the donor or acceptor, and the left charge donors or acceptor that gives electron, and it becomes positive ions. So it becomes a charged donors or charged acceptor. As in the same, that means in the same region, there are charged donors as well as the electrons. This is positive. Now electron is negative, so they have interaction. That is Coulomb interaction. So due to this Coulomb interaction, they can reduce the transport property or mobility. So that scatters the carriers through their Coulomb scattering, and that spoils propagations as well as it can blur energy and disrupt the interference between the electron holes. So this we can face the problem if you dope in the same region where you want electron or hole. Then how we can overcome this? The solution is that instead of doping in the same region, see here, suppose you want electron in this region. So instead of doping in the same region, you dope in a remote or modulate. So solution is remote or instead of this region, you dope in another region, this region. So the doping is grown in one region, you dope here, but the carriers that can subsequently migrate to the another region. So for example, you say here, see here the gallium arsenide. This is aluminum gallium arsenide, where you dope. But our aim is to get the carrier in the gallium arsenide region. So due to, as previously I already told you, in gallium arsenide, if you make a heterojunction between all gas and gas, the all gas has a higher electron affinity. If you compare the electron affinity with respect to vacuum level, this gallium arsenide has a higher electron affinity. So the carriers, that electrons, can easily come to the gallium arsenide region, and they can reside at the heterostructure. See here. The carriers, they can come to here and they reside at the heterojunction at this interface region, and it will bend that the carriers present here will be treated like a two-dimensional. So this will give rise to two-dimensional electron gas. So as you know, now the material is neutral everywhere and the bands are flat. If the electrons sit on their donors on the N gas, you dope here. If the electron will present only in this gas in the donor region, then the energy band became flat. However, due to this difference in electron affinity, the electron will travel after being released, and some of these electron will cross and they can come to the gallium arsenide. As the electron come to the gallium arsenide, they lose energy and it became trapped. Now the electron trap in this region. The electron trap in this region. As the electron trap, now there is a very high band height. This is the potential height. You know, as that there is a finite potential height and it is quite large, the electron cannot again return back to the gas region. So the electron which come from this barrier into the gas into the gas, now there is negative charge, and these carriers which gives electron that left positive ions. So there is a positive ions, there is a negative charge, but they are not at the same position. So they are separated by they are at different positions. So that will generate or it will set up an electrostatic potential hijack due to this positive ions and negative electrons. So now the total energy of that electron present here, that is about the total energy, is the sum of kinetic and potential energy. So that kinetic energy can obtain from band structure. Normally band structure is don't vary with the position. That means when you move along z direction up to this interface, the energy is fixed. Let that let the potential is 220 MeV, so this is 220 MeV. That means this is fixed up to this interface. Then after that, it became 0. So that is the kinetic energy, which is normally fixed in the material, don't vary. However, the electrostatic potential which was developed due to these positive ions and electrons which are trapped in the gas, it can change. So the electrostatic potential that can be obtained by minus E into phi z, this minus E is due to the electron. So you can get, that means if you sum this kinetic energy, this potential plus another potential, electrostatic potential, and then you will see now this energy. So actually there I will show you why there is band bending. I will show next slide. So now the electron will behave here as a two-dimensional electron gas. So what are the advantages we will get due to this modulation doping? The advantages, that means here it is separate electrons from their donors. Donors are in gas, electron is in gas. They are separated. As they are separated, it can reduce the scattering, ionized impurity scattering. That means if scattering is less, then it can give you high mobility. So by using this modulation doping concept, the MOSFET and HEMT devices were made. And also, due to this technique, you are now getting two-dimensional electron gas here. So it also gives rise to DEG. So now, further you can increase the transport property if you add a spacer in between the gas and that doping region. So if you add a spacer layer, it can further reduce the scattering. But you can get a disadvantages you will get that can reduce the density of electrons in this two-dimensional electron gas. In this region, if you add a spacer, the MS, that is the density of electrons that can reduce if you add a spacer. See this one. So as you know, in modulation doping, as already I explained, so there is creation of quantum wells. That means if you think this is a V shape, the V shape, so it will be behave like a quantum well. So due to this modulation doping, there is creation of quantum wells or electrons by doping alone. And the charge can transfer across a heterostructure interface. That means here in algas it became positive charge, here it became negative. And due to this separation of positive charge with that of electron, there is suppression of electron scattering. So that's why this implemented in high frequency devices, particularly in mobile communications, satellite communications, etc. So why this bending that I explained you. So this see this band bending, the energy, band bending energy you can get from the kinetic energy plus potential energy, electrostatic potential. But that kinetic energy is fixed, which is depends upon the band structure. But that electrostatic potential you can get by solving this Poisson's equation, because which is depends upon the rho. Rho is Q into ND. How many number of dopants you go? So if you solve this Poisson's equation, you'll get the V. What is that V? From that V, which gives you the idea about electrostatic potential. So you add that electrostatic potential with the kinetic energy, you will get this band bending. So electron, as already told, the electron that come from this valence algas region to gas due to higher electron affinity, and sorry, the flow of electron from this region to gas, it will continue up to equilibrium is established. That means until chemical potential on two sides are equalized. So it leaves positive space charge behind an algas and a negative charge in the gas region. So we need to solve this to find out what is the electrostatic potential by using the Poisson's equation. So you can see here. So how we can make this band bending? So simply for this is for those who are students. So first you make the flat band with respect to your doping. Let this algas we dope N type, and there is very slight take a this is heterostructure of like a PN junction. You take but this PN N is made up of with algas and P is made up of with the gas. So depending upon the doping, just 1 minute. Sorry to interrupt. Just 1 minute. मामू वो क्लास चलती तो मैं फोन करती और हाँ sorry Devashish sir, my voice is audible? Is my voice audible?
Yes, you are audible.
Okay. So sorry for the interruption. Sorry. So here you can see. So depending upon your doping, you just make a flat band, and let us take another energy ECA bar, which is equal to ECA minus the band offset. You know, you can find out the band offset from the delta Ig, because you know the band gap of this material A and B. So similarly, you just make an EVA bar, which is equal to the EVA that of minus delta Ig. So then when you make the junction, the Fermi level will align. Now, if you apply a positive potential in the B, this material, then there will be mismatch. So you know this is which has less electron, more electron affinity. So and the Fermi level is at a low level. So when you join, the Fermi level will align. As the Fermi level, this B material moves up, this EC that of B material will also move up. So here the conduction band in B material is in the upside and ECA is in the downside. So now this so at equilibrium it will match, but if you apply a field, that means voltage, then there will be a gap of difference EB. So now, now you join this ECA with that of ECB and EBA with that of EBB, and after that you will make the parallel curves, and this bending that can be obtained from the solution of the Poisson's equation. But if you want to find the exact value of this energy wave function and that static electrostatic potential, you need to solve both Fourier's equation and Poisson's equation self-consistently. So here, after that, now we can shift this ECA. After that, you can shift the ECA on side A as line ECA bar. That means this ECA can be shifted to ECA bar and EVA to EVA bar. So the interesting fact you can see here, if you take a normal PN junction, then at the junction there is that means the bands are bent near the heterojunction as they would be in a PN diode, junction diode, but the discontinuity in the bands that are the new features that carries may be trapped in a potential well next to the junction. So here the electron will be trapped. In a PN homojunction, both N side and P side, you can see there is a depletion. The charge will be depleted in a homojunction, PN junction. But here we take the heterojunction, all gas and gas, P and N. But here in one side, the charge is depleted, but in another side, the charge is accumulated. So that is the difference in case of a heterojunction. So this charge is accumulated. So there is accumulation layer of electron on P sides in your gas. So as already I explained, to further improve the conductivity, simply you add a special layer. If you add a special layer, then now the distance between the positive ions which are left in the gas and the electron in the gas, as the distance increases, so what will happen? You know the Coulombic interaction F, which is equal to minus Q1 Q2 by R square, that is 1 by dielectric constant, so that R increases. As the R increases, so F decreases. That means now the Coulombic interaction force, Coulombic force, which is the main factor for ionized impurity scattering, that further reduce. As it further reduce, it can improve the mobility. But you can get a disadvantages for this. That means maybe the number of carriers, that means the electron concentration in this region, that may reduce. But the mobility can improve very prominently. So for the first time, the PFR group, they have obtained the mobility of electron up to sorry. Up to that there is a small bar actually. How can move it? Okay, they got a very high mobility due to this modulation doping. Specifically, such structures they used to observe the quantum and fractional quantum effect, and as the basis for room temperature high frequency transistors, this MOSFET structure. So technically, the high channel transconductance, because here as mobility is very high, and also you can improve the doping. You can add a high doping. So due to high mobility and N, the channel transconductance that increases. So this is the reason for excellent high frequency performance and important present day application in mobile communications. So till now we are using this HEMT and MOSFET for high frequency operation. Right now the GAP is the prominent one. So by using the modulation doping concept, we can design the, as already I explained, the HEMT or MOSFET, the field effect modulation field effect transistor. So here the electrons, they are intentionally separated from the donor and they are confined to a triangular like quantum well. near the heterojunctions, and that gives rise to the two-dimensional electron gas. So you add the gate and source and drain, and the channel is this. You can get very high speed operations. So you can see just yesterday that we discussed regarding in case of SiO2 and silicon interface, you can also get this 2DG just like in your gas structure. So here, as in the interface, this is V shape. That means the electron motion along this Z direction is siege, so it can move only along this direction. So as a result, the energy is quantized. That means you can get discrete energy levels. So the electrons which are below the Fermi level, they will contribute for the transport property. That means they will contribute for conduction. So this shaded region that represents to the electron with the extra kinetic energy, which is for moment perpendicular to the drawing. That means they can move this direction perpendicular to this surface. So by using the same concept, the HEMT, which is on a high electron mobility transistor, where you apply the gate, source, and drain, but only instead of silicon, you take this heterostructure property. That means here you take a all gas, which is doped. There are undoped all gas spacer, this region, and here is the gallium arsenide buffer. So as explained earlier, so you can get the electron in the interface between all gas and gas, and you can control the movement of electron in this channel from source to drain by using the gate. So this is the HEMT technology. And nowadays, as I explained earlier, this conventional gas and all gas HEMT technology, which is very prominent one, but right now, nowadays, the most important HEMT technology, the material is on GaN, the nitrate material, because the nitrate material, which is a high band gap material, so it can give very good thermal property as well as the transport property in GaN. So in gas or gas, if you want to get this 2DG, you should intentionally dope. If you dope the barrier, then you can get the electron in the channel. That means in the interface. But in case of GaN and algan, so even though you are not doped in the barrier, you can get carrier. You can get electron, free electron that in the interface. And this electron that we are getting at the interface in a algan GaN is due to the surface traps or surface charge. So as it is asymmetric in nature, so due to surface charge, you can get the carriers at the interface. So in case of this algan GaN, there is no need of doping to find the 2DG, and you can get a higher shift charge and a higher conduction band in discontinuity, particularly in GaN and algan. So particularly the 2DG, the MS, two-dimensional density at the heterostructure interface in GaN algan is order of 10 to the 12 or cm square, whereas in case of gas, maximum it will be 10 to the 11 order. So you can get high doping concentration, high two-dimensional electron concentration at the interface. So that I already explained yesterday regarding quantum well. So as all of you know, you can make a quantum well by taking to large band gap material. If you confine a low band gap material in between to large band gap material, and in a coupled quantum well structure, this splitting of energy levels takes place, and that splitting of energy levels is due to the confinement effect as well as the coupling effect. So now we go for the this heterostructure property, which is huge in our transport improvement of transport phenomena. So there is long journey from infinite interface recombination to ideal heterojunctions, specifically which was started with the lattice match heterojunction from 1959 onwards. So uh, they have got Nobel Prize. Already I explained these things. So here, if you see in case of a heterojunction HPT in as compared to normal BJT homojunction, and if you take a heterojunction HPT, the property and the transport property is quite far better as compared to that homojunction. Similarly, as explained by the heterojunction by taking algae and gas. So it was reported if we use this heterostructure property, then drastically we can improve the transport property. So let's go for the quantum effects. So what is the quantum effect that will see? So the quantum mechanics apply to heterostructure, that basic quantum mechanics as applied to carriers in heterostructures, that will give you the effective mass theory and the Dinger's potential energy landscape model. That can be, for example, you can take the potential state, potential wells, and quantum confinement structure. So that effective mass theory is very useful one. You can see just that we have learned from the graduation level. That means see. So, for example, if you take that means a simple quantum well that I explained here. So here this region is all gas and this region is gas, the oil region. So here, so as per the effective mass theory, that means here the mass is different inside the channel or inside this oil, the mass is effective mass is different as compared to all gas. And when we go for this boundary condition, that means the if you see, if you take a very infinite oil, if you take a infinite oil, that means the energy is confined, the electron is confined only within the boundary. That means to get the electron, the probability of getting electron outside this boundary is zero if this is infinite, if the potential height is infinite. But if you take a finite height, then there is some probability that can tunnel or that can come to the barrier, this region. So when we go for the mathematical analysis, that means we use the boundary condition. That means there is a discontinuity at the boundary, and at that time we use this property, the mass, effective mass. That means the mass in the oil is different and that of mass in the boundary, the outside the oil, that is barrier, which is different. So and also we can go for this low dimensional orders like 2D, 1D, and 0D, that gives you the quantum oil, wires, and torque, and their energy level system, and we can find out what is the density of states. So in real world, the real world issue is the finite barriers. So normally for theory we read infinite barrier, but for real life applications we take the finite barrier. Then effective mass changes in the oil and barrier, then the non-parabolicity, multiple bands, and strain. So these are the real world issue which we have already covered, is regarding strain, the effective mass. So let's go for the calculation of this density of states, which is an important parameter for to know the transport as well as optical property. So as per the effective mass theory, electrons in the conduction band of a nearly perfect semiconductor lattice can be modeled as they are moving in free space but with a different mass, which is known as the effective mass. So their wave function satisfies the Schrodinger's equation with an appropriate mass and potential energy that can be expressed that minus h cross square by 2n star del square psi by del x square e minus, which is equal to e minus v of x psi. Psi gives rise the distribution of the electron. So E is the energy, V is the potential of the wave. So this m star, which is the effective mass. So similarly, we can design it for empty valence bands that can be modeled as positive charge particles, that is holes which moving in free space with their own effective mass. So in heterojunction, as per the potential energy landscape model, in heterojunctions, electrons and holes that can be modeled by the effective mass theory, even though perfect periodicity is destroyed. In this case, the potential energy profile Vx seen by electron is Ec of x, and that seen by hole is V of x. That means when you take a quantum wave, so the effective mass, the perfect, that means the potential energy profile that can be seen by the electron. That means just I plot in the last slide. So that means if you make this, this is quantum well, and this is the barrier. So the electron which is present here, that means if the electron present here, you can see the energy is this one, that is Ec. Similarly, the hole which is present in the valence band, you can see the energy is Ev. So that means when you reduce the that means the dimensions that semiconductor, that means the high dimensions of the width is quantized, then we get the heterostructure or quantum oil, multiple quantum oil superlattice. So which is 2D structure. If we reduce the dimensions, 2 dimensions, that means the motion along 2 direction is siege, then it became a 1D structure like your quantum wire, nanotubes. And if you quantize it, the totally the flow motion of electron, that means the motion along x, y, z is siege, it is quantized, then we say it is a 0 dimensional like quantum dots. So for this, our aim is to know the density of states that gives rise to the property, transport property, which is an important parameter, the density of states. So as starting of this today's lecture, I have already give you gave you the idea regarding the billion zone. So let's this the first billion zone. So here a single band has a total number of like n states, but the whole n state has not filled. So only a fraction of states are occupied. Then question arises, if we take a specific energy, up to that energy, how many states are occupied? So our aim is to find out this. Or equivalently, we can got the answer if we go for the density of states. That means how many states for unit energy. So we go for the remember an interesting fact. This k. So this k is the wave vector. We say this k. So what is the value of k actually? We see what is the value of k. So you can see here the value of k. So see here this k, which is very interesting parameter. Suppose this is a one-dimensional. So the atoms are arranged. Let there are n number of atoms. Here there are n number of atoms, and the spacing between two atoms is a, the atomic spacing. So if you go for the first billion zone, then there is a minus pi by a to pi by a, this k value. So what is that k? So as it is minus pi by a to pi by a, if we consider only the first billion zone, then what is the maximum value? The maximum value is pi by a. So this a is nothing but that lattice constant may be maximum. Let it be 5 angstrom. If it is 5 angstrom, now the k value is equal to 0.2 into this angstrom. So which is 10 to the power minus 10 meter. So 0.2 into 10 to the power, that means minus 9 meter. Sorry, plus 9 into pi. So see, this is the a very large number, the value of k. So that means maximum value of k at here is this, or up in the meter inverse. If we say this is in meter inverse. So let we make a one-dimensional structure having the interspacing between this. If you take, that means the delta k, the gap between 2k is 2 pi by na. So here this 2 pi by na means 2 pi. Let n is the number of atoms. Let it is order of 10 to the power 22. Order of atoms. Let it is 10 to the power 22 into a. So this a, which is 10 to the power that we what it, let 5 into 10 to the power. So minus 10 meter. So you see, that means in between this brilliant zone, that means from this 0 to pi by a, how many that means k you will get, and what is the spacing. So the spacing is very close, very close. So we can find that number of states either by considering the E space, energy space, or by K space. So if you take this, if you probably if you take energy space, take a small zone between E1 to E1 plus delta E. Now within this zone, how many number of states are there? That gives you the density of states. If you want to find out the, if you consider the K space, then take this one, let K1 and another one K1 plus delta K. So within that K1 to K1 plus delta K, how many states are there? So it depends upon our analysis, whether we will consider the energy space or K space. So let's go for bulk material. As you know, for a bulk material, that is three-dimensional. For a bulk material, the volume in K space, let the distance between two atom, let's take it L, so 2 pi by L cube. The dimensions that we consider, not atom, 2 pi by L, the dimensions is L. We take a width of L, so 2 pi by L cube in three-dimensional, the volume. So volume in K space occupied by states with energy less than E is how much? So if the volume in K space per state, then volume in K space occupied by state, the total volume, as it is three-dimensional, so it will be 4 pi K Q by 3. What is that K? So you will get this K from the this Schrodinger's equation. So where this K, see, if you simplify this, if you simplify, then del square psi by del x square equal to, that means E minus, that means this minus s cross square by 2m star to this right side, and you can make a second order differential equation. Then from there you can get the value of k, which is equal to 2m by h cross square E minus ec. So so the number of electron states, which is equal to the volume in K space divided by the volume in K space per state, that will give you the number of states. This 2 is multiplied as per as we consider the spin up and down. So 2 is due to spin. So if you simplify this, you'll get the expression for density of states in ball equal to LQ by 3 pi square 2m by h plus 3 to 2 E minus EC to the power 3 by 2. That means the density of states depends upon, is directly proportional to that of E minus EC to the power 3 by 2. So that is number of electron states. Then the density of states with energy, if we consider the E space in between E and E plus T, that will give you the 1 by volume, which is LQ, then derivative of this dNE by with respect to E. Derivative, if you find the derivative, then simply The density of states for three-dimensional will be 1 by 2 pi square. This 2m by h plus square 3 by 2 e minus e to the power half. That means the density of states is proportional to the uh, half to the power of that of energy E minus conduction band is C. Similarly, if you go for a quantum wave, in a quantum wave, one dimensional is we confined, so it can only move along y and z. Let x direction is confined, it can move only along y and z direction. Therefore, in a quantum wave, if we take a quantum wave, the area in 2D k space that will be 2 pi by L square. Therefore, uh, the energy in quantum wave, which is discretized, that can be obtained as pi square h cross square n square by 2n star dx square. It depends upon the thickness of the wave. Is d. Uh, if you take this quantum wave, you take a d, then this dx. So if you change the dx, then the energy can be changed because here energy is confined, and it also depends upon n. As for the basics, if you take n equal to 1, if you take n equal to 2, then the next energy will be 4 times because it is n square. So the number of electrons, therefore the number of electrons in this area, that will be given by uh, the area divided by the 2k space for state pi by L square. So this will give, you can if you find from the calculation the density of states, it is only n star by pi square h cross square. That means it is independent of E. But actually it is not independent of E. It depends upon E with a theta function, heaviside step function. I will show you later. So that I given in a wire, quantum wire. So the distance in k space or state is 2 pi by L. So suppose you take a wire of length L is equal to 1 mm, 1 millimeter. Then in that case, the k will be 2 pi by 3, 2 pi by 10 to the power minus 3. So it becomes 2 into 10 to the power 3 pi meter minus meter inverse. So if you find the number of states, the same procedure, if you find the number of states in a one dimensional, that is quantum wave, you get this depend on E minus ENM minus EC square root of this. This ENM is that in a quantum wave, the N and M direction, they are that direction is switched, it only confined one direction. So similarly, you can go for the quantum box, that is the quantum dot. You see here, I will show you in details. We see for a ball 3D structure, the energy which is equal to the conduction band energy plus, you can see here, as this is for a quantum wave. If you take a ball, see, if you take a ball, then the energy in the conduction band, that energy is equal to the minimum conduction band energy plus h cross square. Let us take the three dimensions x, y, z. So h cross square k square by 2m, k is along kx square plus ky square plus kz square. Similarly, if you take a two-dimensional, now one dimension is siege, therefore the energy is equal to EC plus EN. EN means along this direction, the motion of the electron is siege, plus the free direction, which is along these two directions, two dimensions, h cross square, k is now kx square plus ky square by 2m. This En, which depends upon the length of the quantum wave and the number of n. So which is along this direction, the energy is quantized. So it gives you the subband structures, and the same thing that will be applicable for poles. So if we make a recap that we have derived for a three-dimensional, the density of states, which is equal to which is proportional to that of E minus EC to the power half. And in case of 2D, as already I told, that which is equal to A pi pi square h cross square, and it is depends upon the Heaviside step function theta, that summation over theta E minus EC minus En. That means depending upon the n, depending upon the Heaviside step function means when E match with EC minus En, then it will be 1, otherwise it will be 0. Similarly, for 1D, the energy dependent is to the power minus half, and for 0D, it is depends upon the delta function. That means it is only a line in a 0 dimensional. So here, this NMP, that may be 1, 2, or 3, that subband indices, and theta, which is the Heaviside step functions. You can see, if you take a quantum well that I explained earlier, this is the in this for a the dotted one, which is for a bulk. That means if it is bulk, it is depends upon e to the power half. So it is semi dependence is this. However, in case of a 2D, it depends upon m by pi x square with a Heaviside step function. So that's why this density of states is like a step. When the energy, this is E, when E match with that E1, that is E0, E1, E2, when it will match, then there is a step. Then it will move. Then when it match with E2, then there will be another step. So this is a step function. In case of a two-dimensional structure, you see this for a three-dimensional, it is a e to the power half. So that's why this is the dependence for bulk. Similarly, for a 1D, as I shown, if it is one-dimensional, it is the density of states depends upon the e to the power minus half dependence. So this is the distribution of density of states. And for a 1D, that is quantum dot, it is depends upon the delta function. That means when you get a energy, there is a sudden spike delta function. So there will be one that is at E0, then at E1, then at E2, like this. So these are the density of states. So as I explained, in bulk energy, which is h cross square k square by 2m square, and you can take k equal kx for ky kz. So, however, if you take a two-dimensional, now this kx, the k is equal is a function of kx and ky, and motion along z direction is ch. So the e to b, which is equal to ez plus this h cross square kx square by 2m star, and you will get this quantum well. So now the electron can move. That means along this z direction, this ch, it can move only along this xy direction. Similarly, if you take a wire where along y and z direction it is ch, the motion along y and z direction ch, and it can move along only x direction. So the energy is h cross square k square by 2m star, and its corresponding density of states. So similarly, for a one-dimensional, which is equal to exyz, that means it is fully quantized. So this is the gist that we go for density of states. Then another one, the last class I already told, you can get the idea about distribution of Fermi direct distribution function will give you the probability of occupancy. And so here, in case of a bulk, the density of states. In case of coil, it is just like a step function due to the theta function, Heaviside step function. And in 1D, it is proportional to the e to the power minus half. That's why when E match with E0, because it is discretized, when energy match with E0, then this will be gradually reduced. Whereas it is e to the power half, so the density of states increases. So this green one gives the Fermi energy, and depending upon the density of states and Fermi energy, which is gives the probability, we can get the carrier concentration n. So let's just the last discussion regarding this Fermi direct distribution function, which is also important one for to know the transport property. So as you know from the Pauli exclusion principle for fermions, if you see it restricts the occupation number of a state to be either 0 or 1. That means if we say the average occupation is governed by Fermi Dirac distribution, that is equal to e to the power e minus cf by kbt plus 1 to the power minus, that is a whole power minus 1, that is 1 by actually. So this Fermi Dirac distribution is a function of energy, Fermi energy along with temperature. So if you see, if you plot this energy versus Fermi energy at a different temperature, you see when temperature equal to 0, here we take the Fermi energy 10. This figure is taken from this Davis book. So if Fermi energy is 10, at t equal to 0, there is a step. The Fermi function is just like a step. Whereas as the temperature increases, you see 10, 30, 100, 300K, as the temperature increases, now it becomes more slanting. For a high temperature, it is totally slanted. So that you can say the Fermi distribution function that can be lies between 0 and 1, and it is always greater than or equal to 0, half, that is 0.5 when E equal to EF. Here I have shown it is exactly half. So it also interpreted as the probability of the state being occupied, and it is a decreasing function of energy. As energy increases, this decreases. So it is a decreasing function of energy. That is, a state is more likely to be occupied if its energy is lower. And the transition from 1 to 0 that becomes sharper as the temperature lower. When T is 0, the transition from 1 to 0 is very sharp. As the temperature increases, it becomes more slanted. So, and it becomes a Heaviside unit step function in the limit of 0 temperature. That means if T equal to 0, then that for me, probably I will explain about this tomorrow, because what we are doing in our research, normally we are calculating the transport property at a T equal to 0 Kelvin. So when T equal to 0, then it became very simpler to find out the Fermi distribution function, because it became a now theta function. That theta is the Heaviside function, which is 0 if x is 0 less than 0, and 1 if x is greater than 0. So all states below EF0, we say they are completely filled, and above EF0, these states are completely empty. So there are n number of states. But we find out what is the number of states that I explained in the last figure. So here see, this is the density of states, but all states are not occupied. It depends upon the Fermi function. Probability, depending upon the Fermi function, Fermi distribution function, you can know how many number of carriers they can take part in the conduction process. So there are some additional issues like the real world issue, like finite barrier height, as I already explained. In case of infinite, no doubt the electron is totally confined. However, it is not possible. So the wave functions, then now when you take a finite barrier height, the wave functions, they can penetrate into barriers, and treatment is algebraically more complicated, but it is straightforward. We can derive the wave function and its derivative that must be continuous at the boundary, at the finite in the boundary of the well, and effective mass discontinuities. That means if masses in OL and barriers differ, this must be taken into account when matching the wave function at boundary. When you match the wave function at the boundary, that means psi at as you know basics from +3 graduation level. That means when you go for the calculation, we say at the boundary, that means when you take this wave function, that wave function at this, let x equal to 0, x equal to L, then we say the wave function normally we assume at x equal to, so here when you take the boundary condition, you should take different mass for barrier and for well. and the non-parabolicity. What is that? If effective mass changes with energy, the correct value of effective mass must be used. This usually requires iteration of the solutions, another unknowing complications. That means if you are energy, that means you can take don't fix the effective mass. For example, take a well, but the effective mass may not be same inside the well throughout the well because your energy varies. If energy varies, then in accordance with energy, you can also calculate the exact effective mass. Then multiple bands. In the valence band, there are typically two hole bands, as explained earlier, the light and heavy hole. So that must be considered, and they may interact if they overlap to complicate the picture. And also the strain, if there is a strain that will shift the light and heavy hole bands and modify the point, that means it can modify the transport property also, this strain. So these are the real world issue. We must that means take a very serious note about all these phenomena. So for today's what we have discussed from the starting, that we discussed about the brilliant zone and regarding this uh, that band gap. Then we discuss about the heterostructure, which is nothing but a new kind of semiconductor material, which are very expensive, complicated chemically and technologically, but most efficient one is the heterostructures. Uh, Modern electronics is based on heterostructure application that already we have seen in your DHS, that is double heterostructures laser, heterostructure photodetector, and right now the OEIC, that is optoelectronic integrated circuit, that only solve problem of the high information density of optical communication system, and also the future high-speed microelectronics that will mostly use the heterostructure, because nowadays commercially there is 14 and 7 nanometer, 14 nanometer, 7 nanometer node length CMOS, but when we reduce the node length, then in that case we should think alternate material where this heterostructure, particularly the third fifth heterostructure, will the prominent material, because in third fifth heterostructure they have higher mobility, higher transport property. Similarly, high temperature, high speed power electronics, a new broad field of heterostructure applications, and this heterostructure in solar energy conversion is also most expensive photo cells and the cheapest solar electricity producer that can be obtained by using this heterostructure. So it has vast applications and it can be implemented in nowadays modern devices, electronic as well as optoelectronic devices. So thank you. So hopefully this will be covered tomorrow, the transport property, and particularly the research, specific research oriented that. Thank you.
Yes, thank you, Dr. Narayan. So I think it's already open. You can, if people can ask the question to Dr. Narayan directly, if you have any question.
Hello.
Yeah, please.
Yes.
Good morning, Dr. Sahoo. It's a very nice presentation. Hello, am I
Thank
audible?
you. Yes, yes, thank you. Actually, I want to just inform,
Yes,
I
please.
don't know you have joined earlier or not, that we have discussed yesterday regarding
Yes,
that 100 and 11 dimensions.
Yes, yes.
So today morning I clarified that this one.
Yes,
Have
yes.
you heard
Yes,
about
yes.
this? Or?
Yes,
Okay.
yes.
So actually this
Thank
one
you,
is
sir.
the correct figure actually.
Yes, sir.
This one that we
Yes.
have discussed. So
Yes,
normally we take
yes.
different picture and for our simplicity to merge it.
Okay. Yes. Thank you very much for
Thank
this.
you. Actually, for yesterday's discussion, that actually I have not idea about this, but I make some search and I
Actually,
got this idea.
first 5 minutes, I missed the video. I mean, of your lecture. So I will go through it when I get the the recorded lecture of your this talk.
Yeah.
So no, I also Google searched it yesterday and got the response for that. Thank you very much for this
So,
kind of, and these things I have already from here, from this window engine I have started, and sorry
yeah.
for that I have missed your lecture for
Oh,
first 5 minutes. I have some question for this. I have some queries. Right,
yeah.
yesterday you have discussed some graphene that is AG armchair based GNR graphene nano ribbon.
Yes,
So,
yes, yes.
and today you have discussed some defined type of band gap, and it is I'm very much excited about that. No, in right now in no books are the general books on the solid state physics, they are not defined this kind of band gap. But nowadays, if you see the defined review papers on the band diagram of the semiconductor, and all of these are mentioned, these three kinds of band gaps are there: type 1, type 2, and type 3. And you have
Yes, yes.
you have mentioned that. I'm excited that the students are going to learn these things not from the book, from their professor. So it's very nice. And now I want to ask that what kind of band gap is this? That is, if you make a junction between graphene and any n-type semiconductor, for example, if you take a n-type TiO2, so
Okay.
what kind of band gap is that
Okay.
in between
So,
these three?
okay. So, thank you for your that means meticulous observation. So, just for your clarification, let me explain. Is my screen visible?
Yes, yes, sir. Yes, sir.
So actually, when you want, if you want to make the graphene, that means the RTD, regional tunneling diode, you first design the oil and barrier. So specifically, that means which type of oil and barrier you can design. Depends upon your designing. That means designing factor. Here, as I have shown here, so that means through certain technique, you can take any carbon atom here, and you can design any type of shape. So specifically, if you see here, so this is a simple quantum oil by changing the that means modulating the structure. So when you want to make a contact, that means a graphene with that of like n-type. Actually,
N-type
in graphene,
semiconductor.
yeah. Well, actually, there is no need to make a contact between n-type semiconductor because graphene itself has a good conductivity. Only it needs to make the contact, that is the metallic contact. When you make a graphene, that
No,
means
if I try to make a contact between graphene and semiconductor, so in
yes,
that case, what will be the type of that junction? Type 1, type 2, or type 3?
it totally depends upon how much band height or how you have designed this graphene structure. So depending upon your graphene structure, that is, for example, here we have made this height around, that means this height is around 290 MeV, this height. So it depends upon that how you tune it. So depending upon tunability of graphene, that you can get specifically in general application, we make it type 1 because for transport property, if it is type 1, then we'll get good transport property. So normally we try to actually till now we have not
Can
make
I,
any contact.
sir, can you go to
Yes.
the slide where you have mentioned the type 1, type 2, type 3?
Okay. This one
No,
or this one.
no. Yes, this one,
This one.
the
Okay.
earlier one, 20,
Yes.
75. 75, sir, the earlier one.
75. Okay.
Yes.
This one.
No, Just before that, sir.
This
Sir,
one,
just before, no, just before that. Yes, the 73, I think. Yes,
is for 73. This one,
yes. 73, sir. Yes, this one, sir.
this one.
So here so I have a confusion regarding that. So I didn't find what kind of, so if the graphene is in left side and the semiconductor is in right side, so what
Yes.
kind of band gap is this? So I
Uh,
am also a little bit confused about this thing.
Actually, for that this work, this band gap of graphene that, for example, see if you take a gas and oil gas, so depending upon the band gap, we say whether it is type 1, type 2, or type 3. But when you make a contact between a graphene and a semiconductor, so the graphene, that means graphene itself, how you can make a graphene? Graphene is just layer structure. So graphene is a layer structure. So that band gap should be tunable. That means depending upon our application, we can tune that band gap.
If we use the
Uh,
reduced carbon oxide,
Sir,
sir,
sir, let me.
okay.
So, actually, as per your questions, this first of all, this graphene has zero band gap.
Yes.
When we apply the electric field, then we tune the band gap. We can generate the band gap. So specifically, the band gap in graphene is very low, very less band gap in graphene. So I think Madhusudan, are you there? Actually, this graphene is this is our
Yes, sir.
collaborative
Yes, sir.
work, and Madhu is doing this designing part. So Madhu, can you answer this?
Okay, sir.
Sir, Devasis sir,
Am I audible?
Devasis sir.
Yes, sure. It's good.
Yeah,
Good.
Madhu,
Please.
you just
Yes,
join.
yes, sir. Actually, this is a good question that Dr. Devanjan asked actually. Actually, sir, we can treat graphene in two types. Like if we make a bulk graphene, then that is a conductor. We call it semi-metal. But if we take a strip of graphene, that is a graphene nanoribbon, then
Yes.
and if that is of armchair edged, then
Yes.
that will be a semiconductor, and that will have a defined band gap. As Narayan sir also mentioned, we can also have band gap in graphene by field biasing. We call it field doping. Means if you apply electric field, then you will get a band gap. But that can be done in bulk graphene layer. But that is not a very clever way to do to sustain the band gap,
Okay.
to retain the band gap. But yes,
Okay.
okay. But to get a particular defined band gap, we have to reduce the means graphene is two-dimensional, na? So let us cut it from two sides. Means just make it a channel kind of structure, narrow strip. So as the narrow means as we make it more and more narrower, the band gap of graphene nanoribbon will increase. But when we are asking for a contact with a bulk semiconductor, that depends on the size of graphene, as Sarah already mentioned. If you want a graphene and semiconductor contact, that is a different thing, and sometimes that is a very tricky way because graphene is biotic, na? So if you make any contact, graphene got doped. So that reason that particular junction needs to be specially taken care of. Graphene will get doped actually because it has free carriers. So, and if you take a graphene nanoribbon, then that will have a particular band gap, and you can treat these kind of diagrams like heterostructure kind of thing.
Okay,
Till now, I think people, okay.
Yes, sir. Yes,
And
please.
if you aim to make any device, if you are aiming to make any device using graphene, then no need to make semiconductor and graphene junction because graphene is there, and that's why because we are trying to replace semiconductor with graphene. We can dope graphene itself to make it in type. We can make graphene junction itself. So people always try to avoid these kind of devices like graphene semiconductor junction.
So just a minute,
Yeah,
Madhusudan.
we can do that is graphene
Yes,
metal
sir,
junction.
something, sir,
Yes.
is something. Dr.
Madhusudan, so
Yes,
just I add to one thing.
Okay.
Graphene is used as a contact material or as a semiconductor material?
Sir, both, it can be used for both, sir. Graphene,
Okay.
when you use without creating any band gap, people widely using it as a contact for this
Yes,
timing.
that part I know
For
actually.
this timing, people is using it as a contact. Yeah, but we are trying to develop semiconductor properties in it, within it, so that like different, when we are modeling a current flow, that is IV characteristics in any devices, there we have to take care of strain, that kind of I think those current flow, no carrier or move
Madhu,
in.
your voice is breaking.
He
Okay.
has maybe network problem, so he cannot do
Oh,
anything for this.
So as far
okay,
as
okay,
Anyway, I think
got-
answer already got. So
Yes,
thanks,
yes.
Madhusudan. Yeah.
okay.
Thanks.
Thank you, sir.
So, sir, can you please go to the slide number 92?
Okay. Yes, this.
No, not
This one?
this. Sorry, sir. Sir, it was a, sir, it was 89. Sorry. Yes, sir. Sir, here you have shown that that is the barrier height of the algan. So barrier height is which one? This the left one or the adjacent to the junction of J again?
So the barrier height is at the junction of this interface algan and GAN. Here, this height is when we make a contact. When we give a metal contact, that means
That is
then
that is not the barrier height. I mean, so I'm curious about that. Which one is the barrier height? That is at the junction. Barrier height is known as the junction. I mean, the barrier crossing of the barrier of the hole or the electron at the junction. So it will be at the junction or at the left side.
normally in our work, that means as per my knowledge, we always take this side.
Exactly. Yes.
Is one material, this is another
Yes.
material.
Yes.
So at the interface, interface of the GAN and algan, this is the barrier height.
Okay. Yes. That is the barrier.
Yes.
So why such kind of bending is there in algan? That kind of, I mean, the negative slope kind of bending
This
in
negative
algan.
slope.
Yes. In
so
this part. This one. Yes.
So this negative slope, as already explained yesterday, simple, just like mass concept. This side is metal. You can see also here this negative slope. So there is metal, and this part, this algan. So as due to the difference of their work function between metal and algan, and there are that means the surface charge which appear across the algan, and that when we solve the Poisson's equations, then this potential will reduce.
Yes, that is a quadratic
So,
equation as far as I know. I mean, that should be a term that is not a straight line. It is a kind of bending is there.
Actually here that means you are saying like this gas or gas.
Exactly. Yes.
That this bending here I only considered some maybe yeah. That means because when we solve the Poisson's equation, then this energy gap, kinetic energy plus this electrostatic potential, it will be added with here. So, that maybe here there will be actually it missed here. Thank you for this.
Or any? Can I ask two more questions?
Yeah, no, yeah, it's
So,
good.
sir, slide number 80.
80. This one.
Yes, okay. The next slide, sir, 81.
Okay.
Yes. So, as so what is the equilibrium Fermi level, sir? Okay.
That
Sir,
equilibrium for
this A, what the, sir, I actually forgot that what this A is means. What does it mean? The A, ECA.
age algas, that means a high band gap material which is having doped with a n-type electron, n-type carriers, and this B is material that is the gallium arsenide. So this band diagram just show about the difference between a homo junction and a hetero junction. That means in a homo junction where we get like a homo PN junction, we get the depletion. There is depletion of charge carriers on both sides. But here, when you take a heterojunction like a algas and a gas, so there is a depletion layer in the algas layer, whereas the charge is accumulated in the. So that is the main motto to show here.
Okay, sir. Sir, one thing I have noticed that in your slide, one of your slide, maybe it is in 84, 83, 84, 83. Yes, sir, 83. One thing is that,
Yes.
sir, first one is that, sir, why there is a, upwards bending in algas? That should be a straight line, I think.
No, actually here,
Yes,
because
that's the left
this one,
portion. Yes, left portion.
this one.
Left portion.
No, actually, oh, this
Yes,
one.
yes, this one.
Yes, yeah. This it will be bent if there will be metal, but if we only show algas,
Okay,
spacer,
okay,
then
there
gas,
is-
then it will be
okay.
straight.
If there
So
is
if
a
there is a
metal,
metal, then it will be more towards the upside. So if it is no metal, then it will be straight because this side is doped. Bending will start from this region in the spacer region.
okay, sir, what it, sir. So that means we have to consider left side there is a metal is there. I mean, if
Yeah.
there is a metal contact kind of things, and
Contact,
as
then
you
it
have
will
be-
as you have mentioned in
Uh.
your 80, I mean in 85 slide. So, sir, you have mentioned word that is the capital in L gas and small in gas. So, what is the difference between this capital N and small n? I think
specific.
I have missed that slide number. That is maybe in 89, I think. Capital N small, capital N L gas and small n L gas. Is there any difference between this kind of doping? I mean, N type doping.
Specifically for doping, we say
should
it is
forget.
N, that may be
forget
small.
that.
Yeah.
I forget that slide number. So, is there any difference between
So
small n and capital?
he wanted to know, I think, difference between the notations, right?
Yes, yes.
Capital N
notice.
and small n. Yeah.
Capital
That
and small.
Maybe highly doped and small doped. Maybe I
And
don't
that
know.
due to this, due to the difference in doping, we make one is capital N, another is small n, maybe for this.
So that N plus plus is the for the
Yeah.
N plus
Yeah.
or N plus plus for the.
Yeah. This is actual right notation. If you make it N plus plus, that means heavily doped. It is N. If it is
Yes.
only N, that is slightly doped. Yeah.
Is there any I mean contribution of defect states in this to reduce the M effect?
Actually, yeah, you have explain everything in next class during our
Okay, fine, sir. Okay,
topic.
fine.
But
No
just
problem. No problem.
no, just I will say you here.
Yes.
What is the perhaps that a good point you have noted? Specifically, we got this in hem structure, MOSFET structure. That means this side is algas. As it is algas, if you increase the alloy concentration in the barrier, then what will happen? After certain concentration around 0.42, this algas became indirect semiconductor. So when the alloy concentration increases, normally instead of this electron coming to gas, some of the electron will be trapped here. There are DX center known as the DX centers or trap level. So some electron will be trapped in the barrier. So it will reduce the carrier. That's why it will reduce the carrier concentration, that two-dimensional concentration, and also it can reduce the mobility due to that DX center. So people are doing in different technique to reduce particularly that trap or DX center. So you should take care of this when because we can't increase this alloy concentration very rapidly because because if we increase X, the band offset increases, the band gap increases, but it is not the right way.
You have showed that nicely in last yesterday class. that's showing the PowerPoint presentation. That's very
Okay,
nice. How the
I think we need to stop here. Okay.
yes.
So
Thank you, thank
it's
you,
already
sir.
1:30.
Thank you,
Thank
sir.
you very much.
So
Thank
all of
you.
are
Thank you,
hungry, very all of are very hungry. So I left
Thank you, sir.
yeah. Thank you, Devanjan, Narayan, and Madhusudan.